Welcome to the class. Now we will see some examples on real cycle. Here we know by meaning real cycle we will consider the losses in the combustion chamber, losses in the heat exchanger, and also we will have efficiencies of turbine and compressor. So this part would have the pressure ratios for turbine and compressor will be different. So let us see how to solve some examples related to real cycle. First example states that an oil gas turbine installation consists of a combustion chamber and turbine. The air taken in at pressure of 1 bar and temperature 30 degrees Celsius is compressed to 6 bar with an isentropic efficiency of 87%. Heat is added by combustion of fuel in combustion chamber to raise the temperature to 700 degrees Celsius. The efficiency of turbine, which is isentropic efficiency, is 85%. The calorific value of fuel is 43 megajoule per kg. Calculate for an airflow of 80 kg per minute. Neglect the effect of fuel in mass flow rate. Calculate air fuel ratio for the gas turbine and also final temperature of exhaust gases. So these things we have to calculate. This is a simple part of the example, and here we have to also find efficiency of the cycle. So now we will start solving this example. A point to be noted here that Cp of air is 1.005 and gamma of air is 1.4 and Cp of gas is 1.147 kilojoule per kg Kelvin and gamma of gas is 1.33. So the specific heat and specific heat ratio for air and gas are different, which we had not taken in case of perfect cycle. So having said this, we will go ahead and solve the example. As per the example, first let us plot the TS diagram, and in the TS diagram we will have 1 to 2 dash as isentropic compression, 2 for real compression, 3 is the T max point or maximum temperature point, and then we have 4 dash as expansion and 4 as real point. So having said this, we know what are the given things to us in the example. We are told that in the example P1 is equal to 1 bar, T1 is equal to 30 degrees Celsius, so it is 303 Kelvin, and then we are told that pressure ratio, which is R compression, Rp C is equal to 6, and then compression efficiency, isentropic efficiency of compressor is 87%, so it is 0.87. T3 is equal to T max is equal to 700 degrees Celsius, so it is plus 273, so it is 973 Kelvin. We are told that turbine efficiency, isentropic turbine efficiency is 85%, so it is 0.85. Calorific value of fuel is 43 megajoule per kg. Calorific value is amount of heat liberated when 1 kg of fuel is burnt, and we are also told that mass flow rate of air is equal to 80 kg per minute, so it is 80 divided by 60 kg per second. So knowing this, we can proceed and solve. First we are told that compression pressure ratio is 6, so we can find out T2 dash. So T2 dash is equal to T1 into Rp compressor pressure ratio for compression bracket raised to gamma minus 1 upon gamma. Here we are told that gamma is 1.4, so we can take it as 1.4, and then accordingly we can calculate. So, it is 1.4 minus 1 divided by 1.4. So, T2 dash comes out to be 505.5 Kelvin. Now, we have to find out T2. So, for T2 we can use the efficiency of compressor. So, compressor efficiency is ideal work input divided by actual work input. Ideal is related with T2 dash minus T1 divided by T2 minus T1, and it is 0.87. So, this is equal to T2 dash is 505.5 minus T1 is 303 divided by T2, which is unknown, and T1 is known, and this gives us T2 is equal to 535.8 Kelvin. Now, we should know here that actual relation for heat addition is m dot A plus m dot F into Cp of gas into T3 minus T2 is equal to m dot F into calorific value of fuel. So, this is the total amount of heat liberated by burning the fuel, and this heat is received by the mixture of air and fuel to raise the temperature from 2 to 3. But we can neglect the mass of fuel in the mixture, just keep mass of fuel in calorific value to find out the fuel flow rate, and it is stated in the statement of the example also. So, we can have m dot F is equal to m dot A into Cp of air into T3 minus T2 divided by calorific value. So, we have m dot F is equal to m dot A, which is 80 divided by 60 kg per second into Cp of gas, and Cp of gas is known to us, given as 1.147 into T3, and T3 is maximum temperature, which is 973. T2 is calculated 535.8 divided by calorific value, which is 43.1, but 43.1 is in kilo megajoule per kg. So, we have to convert it into kilojoule per kg, and then this will match with the unit for the Cp, and this gives us mass flow rate of fuel as 0.0155 kg per second. So, we will get air fuel ratio as 80. Air fuel ratio is practically mass of air divided by mass of fuel. We are neglecting mass of fuel in the total mixture. So, also we have used total mixture mass is 80 by 60 for convenience, but for calculation of air fuel ratio we have 80 by 60 divided by 0.0155, and this gives us air fuel ratio as 86, and this is one of the answer. Since if we go back, we are supposed to find out air fuel ratio. Now, we will proceed with next calculation, which is exhaust gas. We are not given with any losses for the turbine pressure ratio. So, pressure ratio of turbine and compressor is same as in the example, since we are not told that there is loss in the heat exchanger side or there is loss in the combustion chamber for total pressure. So, for us P3 by P4 dash is also 6. So, from there we can find out T3 by T4 dash is equal to P3 by P4 dash, P4, and that is equal to gamma minus 1 upon gamma, but here gamma is for gas. So, we have to take this point into account. So, we have this also as 6, but gamma for gas is 1.33. So, 1.33 minus 1 divided by 1.33. So, this gives us T4 dash is equal to T3 divided by 6 bracket raised to 1.33 minus 1 divided by 1.33. So, T4 dash can be calculated and it is 623.8 Kelvin. So, we will get T4 since we know turbine efficiency, and turbine isentropic efficiency is given as 85%, and so it is actual work output divided by ideal work output, and actual work output is related to T3 minus T4 divided by ideal work output is related to T3 minus T4 dash. So, we will have this is equal to T3, and T3 is known to us, which is 973 minus T4 divided by 973 minus T4 dash is 623.8, and this gives us T4, which is exhaust gas temperature, as 676.2. and so using the turbine and compressor efficiencies we can find out the exhaust gas temperature. Here this example is little different from the example which we would have solved for the case where we had non-ideal components. In case of non-ideal components we had solved similar example, but there we did not consider gamma and Cp to be different. So, we had turbine and compressor both were handling same fluid, since it has same specific heat ratios and same specific heats, but in this example they are different. So, we can find out W net, since we are supposed to find out efficiency. So, for W net we have mass of air into Cp of air into T3 minus T4 plus mass of gas into Cp of gas into T3 minus T4 minus mass of air into Cp of air into T2 minus T1. So, we have W net is equal to mass of gas is again mass of air, okay, which is 80 by 60 into Cp of gas, which is 1.147 into T3 is 973 minus T4, and T4 is 676.2, 80 divided by 60 into Cp of air, which is 1.005 into T2, and T2 is 535.8 minus T1 is 303. So, we can get W net is equal to 142 kilowatt. So, overall efficiency is equal to W net upon Q in, and we know it is 142 into mass of fuel into calorific value, and so it is 142 mass of fuel is 1.0155 into 43.1 into 10 to the power 3, and this gives us efficiency as 21.25%. So, this is the takeaway from the present example, where we have to consider the Cp and Cv to be different for the compressor and turbine, and then accordingly we have to calculate. So, we will move on to the next example, and next example states that following data refers to a gas turbine set employing a regenerator. Isentropic efficiency of compressor is 82%, mechanical efficiency is of transmission is 99%, pressure ratio is 7:1, pressure ratio is 7:1, maximum cycle temperature is 1000 Kelvin, combustion efficiency is 97%, calorific value of fuel is 43.1 megajoule per kg, air mass flow rate is 20 kg per second, regenerator effectiveness, regenerator is heat exchanger and its effectiveness is 75%, regenerator gas side pressure loss, gas side means at the exit of the turbine there will be gas which is giving the heat to the air which is going to the combustion chamber. So, there the pressure loss is 0.1 bar. Ambient conditions in temperature and pressure are through 327 Kelvin and 1 bar. Isentropic efficiency of turbine is 87%, okay, 85%. Calculate the output, specific fuel consumption and overall thermal efficiency. So, these three things we have to calculate. What we have to assume? Assume that the pressure losses in the air side of the regenerator and consumption are accounted for in the compressor efficiency. So, compressor efficiency accounts for the losses which are in the pressure losses. Compare these results with those obtained with the same plant without regenerator and with regenerator but without pressure loss, and also comment on the results. Neglect the effect of fuel in mass addition and heat balance in combustion chamber, but include it in the turbine calculation. Okay. So, we will go ahead and then plot first the TS diagram for this example and again note down the given things. So, TS diagram says that suppose we have 1 to 2 dash and 2 and then we have 3, 4. Now, we have to remember one thing, since we have to account losses, we can solve this example, rather we need to solve this example in terms of total pressure. So, it is not 1, not 2 dash, not 2, not 3 and not 4. If losses are not given, then the static condition can be used to solve the example, but when losses are given we cannot solve the example in the static conditions. So, it is not 2 dash, not 2, not 3 and then we have not 4 dash and then it is not 4 and then we have not 5 in this side of the heat exchanger. So, given things in the example include compressor efficiency as 82%, we have turbine efficiency as 85%, so it is 0.85. We have transmission efficiency as 99%. Turbine is connected with compressor, so compressor work we will calculate, but that much work is just required for the process of compression, but we need to supply more work to get that work from the turbine. So, we practically would have compressor work more due to the transmission efficiency. So, transmission efficiency is related with net work input and we have pressure ratio as 7, combustion efficiency as 90, 7%, and then we have calorific value as 43.1 megajoule per kg, mass flow rate of air as 20 kg per second, P1 is 0.1, P1 is 1 bar, T1 is 327 Kelvin, and delta P in heat exchanger in gas side is 0.1 bar. So, practically given to us fact is that P4, P04 is not same as P01, and so they are on different pressures. So, we will not connect them, or rather if at all we can connect them, we have to keep some gap, and then that gap would be related to the pressure loss. So, we will solve with regenerator first, and then we can work out without regenerator. So, we will find out first T02 dash, since we are told the pressure ratio, and that pressure ratio, so practically it is for compressor. So, pressure ratio for compressor is known. So, T02 dash upon T01 is equal to, so T1 is basically T01 and P1 is basically P01, is 7 raised to gamma minus 1 upon gamma, and here we will take gamma as 1.4 for air, and we have to take gamma 1.33 for gas. So, this gives us T02 dash. So, T02 dash is equal to T01 into 7 bracket raised to gamma, which is 1.4 minus 1 divided by 1.4, and this gives us T02 dash as 570.2, and we can calculate T02 from here using the compressor efficiency, and it is 0.85, that is equal to T02 dash minus T01 divided by T02 minus T01. So, T02 dash is 570.2 minus T01 is 327 divided by, we have T02 minus 327, and this gives us T02 as 623.6 Kelvin. Now, we can calculate the temperature at the exit of the turbine, since we are known with the turbine efficiency, and we are also knowing the maximum temperature, and that maximum temperature T max is equal to T03, and that is 1000 Kelvin. So, for that we can write down, first we have to find out what is the pressure ratio for turbine. Pressure ratio for turbine is P03 upon P04, but this gas goes out at 04 and then it reaches a state which is 06, and 06 is equal to P01, and then we are told that P04 minus P06 is equal to 0.1 bar. So, we have P04 is equal to 1.1 bar. So, we have P06, P0 pressure ratio for turbine is equal to P03 divided by P04, and so it is 7 divided by 1.1. So, we can take it for T03 divided by T04 dash is equal to 7 divided by 1.1 bracket raised to gamma minus 1 upon gamma, but here gamma will be 1.33. So, we can calculate T naught 4 dash is equal to T naught 3 divided by 7 divided by 1.1 bracket raised to 1.33 minus 1 divided by 1.33. This gives us T naught 4 dash, and T naught 4 dash is 631.6 Kelvin. Now, we can make use of it and turbine efficiency to find out T naught 4. So, we have T naught 3 minus T naught 4 divided by T naught 3 minus T naught 4 dash. T naught 3 is 1000 minus 631.6 divided by 1000 minus, T naught 4 is not known. T naught 4 dash is 631.6, and this is equal to turbine efficiency, which is 0.85, and then we can get T naught 4, and that is 687 Kelvin. Now, we are to work with heat exchanger, and now our heat exchanger is non-ideal. So, we know that effectiveness of heat exchanger is equal to actual heat transfer, and actual heat transfer is T naught 5 minus T naught 2 divided by maximum possible heat transfer, which is T naught 4 minus T naught 2. Now, we know everything, so we can calculate T naught 5. Here effectiveness of heat exchanger is given to us, and that is basically told as regenerator effectiveness as 0.75. So, T naught 5 minus T naught 2, and T naught 2 is equal to 623.6 divided by T naught 4, which is 687 minus 623.6, and this gives us T naught 5 as 671.2 Kelvin. Now, this is useful to us for finding out what is the mass flow rate of fuel. We can use the same formula, which is mass flow rate of fuel into calorific value of fuel, but and then that should be equal to the mass flow rate of air, which is mass flow rate of gas practically, into Cp of gas into T naught 3 minus T naught 5. But this is if combustion efficiency is 100%, but combustion efficiency is not 100%. So, not all heat will rise the temperature. So, there will be one multiplication, which is combustion efficiency. So, we have mass flow rate of fuel is equal to mass flow rate of gas, but we are going to take it as air for the sake of simplicity, into Cp of gas. So, it is 1.147 into T naught 3 minus T naught 5 divided by calorific value into efficiency of combustion chain, and then that will give us m dot f is equal to mass flow rate of air is given as 20, calorific value of gas is 1.147 kilojoule per kg Kelvin into 1000 minus T naught 5, we have just found out 671.2 divided by calorific value is 43.1, but it should be multiplied by 10 to the power 3, since it is in megajoule per kg, and combustion efficiency is given as 97%. So, mass flow rate of fuel is 0.18 kg per second. Now, we have to find out what is the net work. So, net work is always turbine work minus compressor work. So, net work is mass flow rate of gas into Cp of gas into T3 T03 minus T04 minus Cp mass flow rate of air into Cp of air into C02 minus T01. But this compressor work and turbine work we can consider for net work if there is 100% transmission efficiency. Otherwise, we need to supply more power for doing the compressor work, and then that is why we have to divide this compressor work by transmission efficiency if transmission efficiency is not 100%. So, W net is equal to mass flow rate of air plus mass flow rate of fuel into T03 minus T04 minus mass flow rate of air into Cp of air into T02 minus T01 divided by transmission efficiency. And so, we will have net work is equal to 1,222.96 kilowatt, since all the quantities are known to us over here. Knowing this, we can find out specific fuel consumption, and specific fuel consumption is mass flow rate of fuel divided by W net, but generally it is specified as fuel flow rate per hour. So, it is m dot f into 3600 divided by W net, and we can get it as 0.53 into kg per kilowatt hour. So, we can get thermal efficiency as W net upon Q in, and we have 122.96 kilowatt divided by mass flow rate of fuel is 0.18 into 43.1 into 10 to the power 3. So, we have cycle efficiency or thermal efficiency of cycle as 15.8, cycle efficiency as 15.8%. So, this is the solution for cycle efficiency, specific fuel consumption and net work output. If we have, this is the solution for the example for net work output, specific fuel consumption and cycle efficiency if we have a regenerator, but now we are told to work out without regenerator. So, let us find out, and in case when we do not have regenerator, then that means that we do not have any pressure loss. So, since we do not have pressure loss, this is a simple calculation, since we will have turbine and compressor both will have same pressure ratio, since there is no pressure loss in the regenerator. So, we have pressure ratio turbine is equal to pressure ratio compressor, and then that is 7. It does not alter the calculation on compressor side, but it alters the calculation on turbine side. So, we have to calculate freshly T04 dash from T03, it is divided by RPT bracket raised to gamma minus 1 upon gamma, where gamma is 1.33. So, this gives us T04 dash, a new value without regenerator and no loss, as 617.1 Kelvin. So, we can find out T04 from this using the turbine efficiency, since turbine efficiency is T03 minus T04 divided by T03 minus T04 dash, and we will have here T04 is equal to T03 minus turbine efficiency into T03 minus T04 dash, and so we get T04 as 674.5 Kelvin. So we can calculate mass flow rate of fuel a new way, and that will be, since now we do not have regenerator, we have mass of fuel into calorific value is equal to mass of gas into Cp of gas into T03 minus T02, but again we have to consider this with efficiency of combustion. So we have mass flow rate of fuel is equal to mass of gas into T03 minus T02 divided by efficiency of combustion into calorific value. But here, for sake of convenience, we will take it as mass of air, mass flow rate of air into T03 minus T02 divided by efficiency of combustion into calorific value. So we have calculated it, we had given with 20, we have to multiply with Cp of gas. So this is 20 into T03, which is 1000 minus T02, which was calculated as 623.6 divided by into Cp, which is 1.147 kilojoule per kg Kelvin, divided by 43.1 into 10 to the power 3 into combustion efficiency as 0.97, and this gives us fuel flow rate as 0.207 kg per second. So we can calculate W net, which is equal to Wt minus Wc divided by transmission efficiency. So Wt is m dot gas Cp of gas into T03 minus T04 minus m dot air Cp of air into T02 minus T01 divided by transmission efficiency. Knowing all the quantities, we can calculate W net, and then that would turn out to be 1522.37 kilowatt. So we can calculate specific fuel consumption as mass flow rate of fuel into 3600 divided by W net, and specific fuel consumption will turn out to be 0.49 kg per kilowatt hour. We can calculate efficiency, thermal efficiency of cycle or efficiency of cycle as W net divided by Q in. W net is calculated, Q in is mass flow rate into calorific value, and this will turn out to be 17.06%. This example tells us few things. We have solved with regenerator. So there we had implemented heat exchanger, and we know that heat exchanger is generally implemented for increasing efficiency, since it reduces the external heat addition. But we can see here that efficiency with regenerator was coming out to be 15.8, and without regenerator was coming out to be 17.06, which is more. So with regenerator we are getting lower efficiency, and without regenerator we have higher efficiency. The difference was mainly due to the pressure loss, and it was only 0.1 bar. So 0.1 bar has led to the decrement in efficiency of the cycle. So, this has also led to increase in fuel flow rate. With regenerator we have lower fuel flow rate, without regenerator we have higher fuel flow rate. Without regenerator we have network as 51522 and here network is 1222. So, network has also got decreased. With regenerator efficiency has also got decreased with regenerator, and both are due to the pressure loss in the regenerator. So, we have to consider these pressure losses while considering regenerator. This is how we can solve the examples for the real cycle where we have to account losses, and when we are accounting losses we have to consider total conditions while solving the example. Thank you.